Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's look at solving a special group of first-order differential equations called Bernoulli Differential Equations. A Bernoulli differential equation is of the form dy by dx plus p of xy is equal to q of x multiplied by y to the power of n, where p of x and q of x are functions of x or constants, and n is something other than 0 or 1. If n was equal to 1, we could solve it by separating the variables. And if it was 0, we could solve it using a technique for first-order linear differential equations. So how do we solve this type of differential equation? Well, we make a substitution for y and for dy by dx to transform it into a linear differential equation and then solve it using one of the techniques we've looked at to solve this type of equation. Well, what substitution do we make, John? I can hear you scream. Well, we make the substitution u is equal to y to the power of 1 minus n. We can then make y the subject of this equation and differentiate this with respect to x such that we have a substitution for dy by dx. So let's take a look at an example. So let's solve the differential equation dy by dx plus 2xy is equal to x multiplied by y cubed. In this equation, p of x equates to 2x, q of x equates to x, and n, which is the exponent of the y term on the right-hand side of the equation, equates to 3. And so our substitution here will be u equals y to the power of 1 minus n, where n in this case is equal to 3. So therefore u is equal to y raised to the power of minus 2. And therefore y is equal to u to the power of minus a half. And using this substitution, we can differentiate it with respect to x. So dy by dx is equal to dy by du multiplied by du by dx. Using the power rule, the derivative of y with respect to u is equal to minus a half multiplied by u to the power of minus 3 over 2. And this is then multiplied by du by dx. And so substituting y and dy dx into our original equation here, we have minus a half multiplied by u to the power of minus 3 over 2 multiplied by du by dx plus 2x multiplied by u to the power of minus a half is equal to x multiplied by u to the power of minus 3 over 2. So now if we divide through by u to the power of minus 3 over 2, we're left with minus a half multiplied by du by dx plus 2xu is equal to x. And simplifying this further by multiplying through by minus 2 leaves du by dx is equal to 2x into the bracket of 2u minus 1. We can now separate the variables to leave two integrals. So we have the integral of du over 2u minus 1 is equal to the integral of 2x dx. The first integral evaluates to 1/2 multiplied by the natural log of the absolute value of 2u minus 1. And the second integral evaluates to x squared, and we add to this a constant of integration, c. Simplifying this by multiplying both sides of the equation by 2 leaves the natural log of the absolute value of 2u minus 1 is equal to 2x squared plus 2 multiplied by the constant of integration, c. Exponentiating both sides of the equation gives the absolute value of 2u minus 1 is equal to e to the power of 2x squared multiplied by e to the power of 2c. If we now let new constant c1 equal plus or minus e to the power of 2c, we can remove the need for the modulus sign. So we now have 2u minus 1 equals e to the power of 2x squared multiplied by c1. And substituting back in for u, where u is equal to y to the power of minus 2, we have 2 divided by y squared minus 1 equals e to the power of 2x squared multiplied by c1. And simplifying this further gives us our final answer, where y squared is equal to 2 divided by e to the power of 2x squared multiplied by c1 plus 1.